Yes, while it comes up, indeed we are having a very interesting discussion this afternoon, and just wanted to contribute, to fuel this discussion. And it's a pleasure to see young figures in this room because, I'm starting to feel a little bit old, and this is the reason why it's time to think about the future centuries. And indeed, I have a split brain this afternoon because I am involved in this European project, Clean Chemie, but I am also involved in this Société Française de la Science Nucléaire dans la Matière Condensée. And indeed, what I am going to talk about exceeds what is included in this Clean Chemie project. This is the reason why I'm going to talk about on behalf of this SFSNMC. Well, it has been said that in the past 100 years there was a large increase in energy consumption, mainly fueled by fossil fuels. And now the problem is, what about the future? Are we going to see a further inflation, drastic deflation, or some kind of stabilization? Well, the fact is we are facing the climate change problem, and this energy transition has a character of urgency. In green, you see what the emissions should be to fulfill this Paris Agreement. And indeed, the present trend we have now leading us to more than 4 degrees C temperature change with unknown consequences. Let us consider this energy structure. In the past, almost everything except hydroelectricity was fueled by fossil fuels and used everywhere for transportation, heating of our houses, power station to make electricity. For the moment, we have a transition with more and more renewables and nuclear fission reactors. But in the future, once fossil fuels are phased out, the main energy vector will be electricity. And we are going to witness a massive electrification, I would say, of this energy sector. What will be the consequences of this massive electrification? Well, it's difficult to predict the future. But for sure, it will lead to large changes in the use of energy in all sectors, of the economy and society. Some sectors will consume less primary energy. Some others will consume more. New technologies will be developed, some not even imagined today. And this afternoon I can only give you some examples, to explain what I am talking about. If you replace electrical heaters in your house with heat pumps, you are going to consume 3 times less electricity. Good. Now, if you consider the iron and steel industry, presently virgin iron is made mainly on blast furnaces using coal or coke, and in the future it will be obtained by reduction of iron ore with hydrogen, And just to produce this hydrogen, you will consume more energy. No CO2, but more energy. So, for electrical cars, this is the same thing, an electric engine is more efficient than a diesel engine. No wonder. Concerning air transportation, hydrocarbons are very efficient fuels for aircraft, and it will be difficult to replace them. The solution might very well be the production of synthetic fuels called e-fuels, And they can be made like this. Don't forget, I am talking 400 or 200 years from now. You suck this CO2 out of the atmosphere. You produce hydrogen from H2O. You have a Fischer-Tropsch reactor to transform this hydrogen and CO2 into synthetic fuels, and you burn this fuel, and you get CO2 back to the atmosphere. This is not complete utopia because such plants are already under construction now. You see one here in Chile. And a bottle of e-fuel, I took a picture in the last Paris Air Show. Now, what will be the future energy demand? Well, you have to make things simple, so it will be the product of the world population by the average consumption per capita. Concerning the population, you know, the population on the Earth grew rapidly in the past years, but several studies suggest that later in this century, it should stabilize around about 10 billion people. Okay, let's take this figure. It's more difficult to imagine the average energy consumption because the consumption is very different between the different countries. So it may be a lack of imagination, but let's consider the average present European value, about 40 megawatt hours per year per person. If you multiply these two, you come to not an optimistic figure. It should stabilize at about 400,000 terawatt hours per year, and this is just about 2.3 times more than now. Fine. So what might be these future sources of energy? Fossil fuels, they will be exhausted sooner or later, and in any case we want to phase them out, so let's forget fossil fuel. So we are going to use carbon-free energies like solar, wind, and or nuclear fission, thermonuclear energies, and new energies, not to forget, like hydrogen metal energy. I'll come back to that. So, is it possible to use them? I am going to make a stupid exercise. I am supposing that all these 400,000 terawatt hours are provided by each single source, one after another. Starting with solar energy, if you make the calculation, you come to the conclusion that you need 1.6 million square kilometers of solar panels. Okay, this is a caricature because they will not be concentrated in over Europe, they will be distributed everywhere, and in any case the energy mix will never be 100% something else, it will be always a mix. Concerning wind energy, the wind turbines are grouped in wind farms, and a wind farm produces more or less 22 gigawatt hours per square kilometer per year. Fine. Taking this number, we come to the conclusion that we will need 18 million square kilometers of wind farms. This is indeed the surface area of the 48 lower states of USA, plus China, you know. We should not forget that China is just as large as the 48 lower states. But it's a lot. Of course, again, it's a caricature. Renewable energies need to be stored because there are intermittent energies. For example, up to now, the technology is to pump water between different basins at different altitudes. On suitable sites, you can use batteries, you know, lithium, sodium-based batteries, and so forth. Hydrogen will be produced also to store electricity, and especially it will be possible to store hydrogen underground for long term, for example, interseasonal storage, because solar energy and wind energy are seasonal energy sources. But there will be other storage system like this thermodynamic storage, just to give an example I love because I am personally involved in this one, but this is not the subject today. What if all this energy is produced by fission reactors? Okay, fission reactors produce nowadays more or less 10 terawatt hours per year, so we would need just only 40,000 reactors, you know. This is 80 times more than now. And it raises some concerns in terms of availability of this enriched uranium, waste disposal, and maybe risk of accidents, you never know. So the fact is there are new reactors under development to address all these concerns, like for example the molten salt reactor, just to name one, but there are several technologies, considered to make safer and better reactors. Question is, all this development will take some time, and will they come on time to limit global warming? Thermonuclear fusion is proposed, as the end solution, the final solution, And indeed, unfortunately, nowadays we think that these power ratings in 2040, 2050 will be approximately the same as the present fission reactors. So all this development took a lot of time, and indeed we don't see the end of this development. So when are we going to get these 40,000 large thermonuclear reactors? And will they come on time to limit global warming? The expectations are so high that we see now many new companies developing their own thermonuclear technology with the hope to be cheaper and faster than these tokamaks, with quite interesting financing figures. So for sure, a new source of energy is required, and we know which one in this room. It has many names. And as I explained, I have a split brain this afternoon. So this is the reason why I am going to use the term hydrogen metal energy to reflect the fact that we are also involved in this clean alchemy project. Anyway, the name is not that much important. So these reactors will be a safe source of carbon-free energy. Most probably we are going to start at least with small unit sizes in the kilowatt range as distributed generators with no much grid and providing the independence of customers. Thanks to the small size, it will be possible to develop these prototypes quite fast, and they will be produced in huge quantities. It should make the procurement cost of these many reactors reasonable, making possible, low-cost electricity and massive electrification, because this is the goal achievable. So yes, in combination with the other carbon-free energies, because I don't think it will replace everything, but it will contribute to solve this challenge facing us. But now comes a question. Is this new energy sustainable in the long term? Don't forget the title of my presentation, for the future centuries. Not today, not tomorrow, in 200 years, 300 years from now. Is that sustainable? Well, let's have a look. This is a picture, this is a graph coming from Clean Planet. And they claim that this energy should be able to produce 1,000 megajoule, per gram or per mole of hydrogen. So please keep this figure in mind. 1,000 megajoule per mole, it's 278 kilowatt hours. And let's go. Let's consider first that these reactors consume hydrogen, protons or deuterons. If this is protons, we will need 1.4 million tons of hydrogen per year. It's easy, no problem, so this is sustainable. If we need deuterons, we don't make the calculations here, but for sure it would also be sustainable. And maybe we are going to see a synergy between the HME reactors and the hydrogen economy. You heard about the hydrogen economy. It is supposed to produce hydrogen in massive quantities by water electrolysis. And you know that in these electrolyzers, the electrolyte becomes enriched in deuterium. It means that the bleed flow of the electrolyzers can become a feedstock for the extraction of deuterium. And if you make the full calculation, you should conclude that we are going to consume as feedstock for deuterium all the bleed electrolytes from all the hydrogen economy. That's okay. What if we need something else? Because we consume some metals because of fission reactions or transmutation reactions, so the metal we use in the reactor disappears or is transformed into something else. This graph shows the abundance of the elements on the Earth. You know, this is a logarithmic scale according to the atomic number. So you see the abundant elements and rare elements. And I added here seawater with hydrogen, deuterium, and lithium. Palladium. All our history started with palladium, and the production indeed last year was just 210 tons. So for sure, it would not be sustainable to destroy palladium in our reactors. The next metal of interest for us, this is nickel. Production in 2022 was 3.3 million tons, okay? But could this nickel be sufficient to make all the energy? Assume now that we need 1 mole of nickel, not 1 mole of hydrogen, but 1 mole of nickel transmuted to make 1,000 megajoules. It means that for these 400,000 terawatt hours, we would need 84.5 million tons of nickel per year. 84 million tons of nickel per year. So the world production is 3.3. So for sure, consuming nickel would absolutely not be sustainable. Now, if nickel is just a catalyst that is not consumed, then it's another story, and it may be sustainable. Indeed, we should not look at nickel, you know, with this abundance, but more abundant materials like, for example, in this presentation, iron, titanium, lithium, you know, because iron or steel is produced in massive quantities. Last year it was about 2,000 million tons of iron produced. So we should be able to find only 100 million tons for us. It would be enough, you know, 100 million tons out of these 2,000 million tons. So with iron, it might be sustainable. It is sustainable. Titanium. Titanium is not that much used, at least in metallic form, just 260 kilotons last year. But indeed, you may not be aware of that, but titanium is largely used as titanium dioxide as a white pigment. If you take a piece of paper, you know, a white piece of plastic, they are charged with titanium dioxide. So titanium dioxide, we are talking about 7 million tons for example, each year. So titanium is not that rare. So this is the reason why I love all the experiments proposed about titanium. Lithium, you know, I'm not going to discuss the availability of lithium for batteries because we are going to consume much more than what is needed now for batteries. But just to mention that lithium is 5,000 times more abundant in seawater than on land, with 170 milligrams of lithium per cubic meter of seawater. So there are schemes to extract already lithium from seawater, so it is sustainable. As a summary, HME is a new source of energy urgently needed to contribute. But the previous one was okay? not enough nickel. Imagine if we use palladium. I see it. I can show you if you wish. So, thank you. So I said HME is as Ruby said, thank you, merci. HME is a new source of energy urgently needed to contribute to this energy transition and address climate change, global warming. This is sustainable in the long term if the fuel consumed is hydrogen or deuterium. If these reactors consume via transmutation of fission other elements, this consumption should be minimized. The metal used should be abundant ones, and recycling should be incorporated, from day one in the design of the reactors. What is not done in the batteries, by the way, for the moment. So, as an outlook, hydrogen methyl energy for the future might be sustainable, but R&D must be devoted to the feasibility to use abundant elements as feedstock. We need some research to show if it is possible to use titanium, iron, magnesium, calcium, such metals instead of palladium, nickel, gold, whatever. Not to forget, this source of energy is a new one, not known from the public. So, as this is the human nature, public will be reluctant. So we need to develop the social acceptance via communication, demonstration, and education. And under these conditions, HME may become a sustainable source of energy for the many centuries to come. I thank you for your attention.
Thank you, Jacques. We have time for 2 short questions.
Thank you very much, Jacques Ruer, for a very important presentation. With regard to the fuels that you mentioned, you're absolutely right. I want a couple of data points. When we were with Piantelli in January 2015, he was talking about nickel, but then he was referring to a metal that was much, much better. He wouldn't tell us what it was.
Yes, please.
But he wouldn't tell us what it was. But at the same time, he had an element up on his screen, and he was like nodding and winking to it, right? Like this. And it ties in with the story that Mats Lowen had access to a hard drive from Sergio Vicardi. And on there was a whole discussion about Piantelli sent a rod to Vicardi to test. And Vicardi got extremely angry because this rod that was sent to him was iron. Now, when we replicated, what he told us was you have to load the metal surface of nickel by bring it up to a temperature where the hydrogen is dissociated. It creates a magnetic moment. It binds to the ferromagnetic nature of nickel. And then he was absolutely adamant that we had to do this. We had to go through the nickel Curie point as absolutely fast as we could. I didn't understand why, he never explained why, but in my view, you can make coherent matter as long as you have the same thing at the same kinetic energy, making the same de Broglie wavelength, and it will be able to form a coherent cluster. And if you do that, when you go through that Curie point as absolutely fast as you can, they all come off exactly in phase and exactly the same de Broglie wavelength. Same would happen at iron, but at a higher temperature. Then you need the fuel, and the fuel would be your titanium, because it's paramagnetic, it can always be consumed, or any other paramagnetic material.
Lovely, lovely. It means that we need this kind of research, you know, to show the possibility to go in the direction you say. Thank you.
Thank you.
Okay, from my point of view, my origin is like as a farmer. The farmer wants to the real condition, and then our technology is toward normal people, middle class people, but who has the control of the world is top class people. They don't want simple technology. I am going toward simple technology, nickel better than palladium, simple electronics procedure. But I have seen, experienced very big attack. So I am surprised. When I used palladium, I can survive. When I moved to nickel, more simple, the attack against my laboratory was terrible. They even burned my logbook. So I am not optimistic. This is middle class energy. Our will be like French Revolution. Remember, so will be very difficult because we need a jump for maybe 40, 50 million euro a year in total to several billion, because the work to be done to move from laboratory experiment to normal people experiment is giant. So we need such big money now. Who will give us money?
This is a good question. You know, indeed, if you look at if we consume deuterium, we have enough deuterium in seawater on this planet for the next 40 million years at this rate of 400 terawatt hours per year. No?
Maybe, okay, you are right. But the problem
we have
is
to move on, Francesco.
such kind of technology is can be used from everybody in the world, not from the top level. This is the key point. We have to remember this one.
This is the reason why we have to go back to the laboratories to develop that.
Okay, one more short question, please.
Okay, thank you very much for this very complete presentation. I have a small suggestion to go towards a communication in favor of our energy source, that is the following. There has been recently a study by a PhD student of the University of Pisa in the Faculty of Engineering, showing that even if you changes from fossil fuel to renewable source as a photovoltaic or wind energy sources, you have still a huge problem due to the demand during the day. The change in demand during the day. So you have
storage.
You have the peak, and in our condition, in our situation, we for sure have the possibility to go towards photovoltaic and solar energy, but you have not the means at this moment to eliminate this problem. So you have still a huge gap from what is required and what you can have during the peak time. So in this case, our source can guarantee the continuity of supply.
Keep in mind, my speech was about the 200 or 300 years from now. So for sure, at that time, yes, we will have hydrogen economy, we will have hydrogen storage, we will have LNR, we will have, many things we don't imagine today. Okay. Of course, we will have e-fuels. So this is not because something is not existing today or is under development today, but it will not exist in 100 or 200 years from now.
Yeah, but the data related to what we are consuming, we are producing now, but if you have the scenario when the electricity is much more than now, it becomes a mess. Okay? And a small comment to Bob, Franco used stainless steel, not iron.
No, absolutely.
Okay. Thank you. Thank you very much.
Iron, stainless steel, it's always iron. Thank you.